there. Huh? Another sandwich?
No,
The spinner and the family. A spinner contains 5 equally likely regions, numbered 1 through 5. The arrow is spun twice. I have the probability that the arrow lands on a 2 both times. So, if they spin it twice, how many events are there? There's 2, right? Now there's 5 regions in the number 1 through 5. What's the probability of landing a 2 the first time? No. It's 1 out of how many regions? So it's 1/5. Now, what's the probability of it happening again? It's 1/5. So what's 1/5 times, sorry, 1/5. Yesterday I was saying a lot of dumb things as well. And words that are words didn't sound like words. But anyways, we need this to happen and this to happen. The word and should be a prompt for multiplication. So 1/5 times 1/5 is? Yes. So the proper bird, the bird turned the bird. Did that answer your question? You're the man. Anybody else? Jesse? Questions, Jesse? You can text them on the YouTube. Say something. I'm giving up on you. Anybody else? Going once? What? The children? The bottom one? A family. A family has 3 children. Oh, these are good. These are so good. So, I'm actually going to close this because I'm going to need the space. Were these the ones we were doing yesterday? Or, the last time we met, Ricky? These were the ones? Okay. Where'd it go? Here it is. Okay, go. Alright, so a family has 3 children. I'm the probability that exactly one of the children. Thank you for. You guys need to watch what I'm doing because. Not my time. I think I will beat this. But technically everybody is dying. Well, actually, let me tell you, this is interesting. The air you breathe is killing you. Yeah. Why? Okay, because the oxygen that you breathe is actually destroying your blood. It's destroying your blood because it's oxidizing it. So you're actually like oxidizing away. But we take antioxidants, which fix the problem. So hallelujah. All right. So anyways, here we go. Usher. I need to close this. I don't want that showing up. Okay. 3 children. 1, 2, 3. Okay? And we want 2 of them to be girls. So I can have a girl, and a boy. What's the probability of a girl? 1/2. You either have a boy or a girl. What's the probability of having another girl? 1/2. And what's the probability of having a boy? 1/2. So the probability of having exactly 1 boy is 1/8. Correct? For this event, for this specific event. However, you can also have exactly 2 girls if you had a girl, a boy, and a girl. Does that make sense? So I would have 1/2, 1/2, 1/2. That is the 1/8. Is that the only way that I can get 2 girls? No, I can have the boy first. And then I can have the 2 girls. Now, technically, this is supposed to be done with a tree diagram, but I think you guys would be okay with this, right? So here, check this out. Now, think about this. What? Thank you. So, if I go home, you're going to just sit there on your phone all day. Yeah, but you want to have questions answered, and then I have more lecture to give. So, shy. Okay, so to have 2 girls, I need to have a girl, and then a girl, and then a boy, which gives me this. And then I need this, and this, and this to happen, or this, and this, and this to happen. So it's either this, or this, or this. And what does or mean when you're doing probability? Add them. So 1/8 plus 1/8 plus 1/8 is 3/8, and that is the probability of having at least 2 girls. Exactly 2 girls. No. That can happen. Anybody need to see it with the tree diagram? You want to see it with the tree diagram? With the tree diagram, you would say, okay, you'd start here, right? And you'd have I'll start with the boy. So I can have a boy, a girl, the first time, right? So this is the first child. The second child, that means would have to be, actually for the next child I can have a boy. Well, wait, no, this is not right. Just kidding. For the first child, I can have a boy, or I can have a girl. For the second child, I can have a boy, or I can have a girl. Here, I can have another boy, or I can have a girl. Over here, I can have a boy, or I can have a girl. I can have a boy, or I can have a girl. I can have a boy, or I can have a girl. Oh, man, I just made a better song than Rihanna. And you understood mine. Okay? So that's what the tree would look like. Okay? So now, in order to find this, what we need to do is find the routes that are appropriate. Okay? So I'll use green to outline the routes that would be appropriate. Okay? So in order to have 2 girls, let's see here. This route would give me boy, 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 correct? This route would give me boy, boy, girl. This route would give me, if I went this way, I'd have boy, girl, boy. And then this route would give me boy, girl, girl. This route would give me girl, boy, boy, right? Oh, JK. And then I can also have, for this one, it would be girl, boy, girl. And then for this route here, it would be girl. They're horrible. Girl. And this one would be girl, girl, girl. Correct? Yeah? Did I get them all right? Okay, cool. Now, this is a tree diagram, but technically, this, my friends, is the sample space. That is the sample space. That is every event that's possible. The probability of this one happening is 1/8, correct? Well, yeah, technically they're all 1/8. 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. Now, here's the question. Here's a question to you. What is the sample space supposed to add up to? 100%, aka 1. 1, 2, 3, 4, 5, 6, 7, 8. So if I have 8 times 1/8, I get 1. So that is legit. I've done this correctly. Knock on wood. Now, the question they had was, what is the probability of having exactly 2 girls, correct? Well, which one has 2 girls? That one, thanks. This one has 2 girls. Is that? That's a G. This one has 2 girls. This one has 2 girls. So I can have this, or this, or this. So again, I add them up. That gives me 3 8s. Okay? Now here's what's really cool about the exactly 2 girls, not at least 3 girls. If the question was at least 3 girls, then we would add this one as well. But they said exactly 2 girls. Okay? Now, the tree diagram is really nice. Because as you travel through the tree diagram, what do you do with the probabilities? You multiply them, exactly. And if you want to find the probabilities that are out here in the sample space, then you just add them. Okay? Oh my goodness. You know what the worst feeling is though? It's like I feel like my head is so heavy. Like if I would lean one way, I think I would probably like let's stop there. All right, what else do you have? What other questiones? What are the questiones, macaronis?
Oh, I had a question on.
What about W?
Oh,
From here? I am the probability that the middle child is a girl. So then I just go back to what I did already and find out which one had a middle child with a girl. So it wasn't this one, it was this one, this one, this one, and this one. So 4 8, which is a half. 4 8. Yeah. That's what's nice about this. You can answer anything you want from there. What? Oh. Okay. Not okay. Wheel of Misfortune.
Oh, I love that game. Okay, my life.
This P right here?
Where's the other one?
Okay, shut up. Well, look, there's like A, B, C, and then there's A. Oh, that's not an A. Oh my God, never mind. I have the probability that the sum of the 2 spins is greater than 7. Ooh, this one's not fun. So for this one, you'd want to create your sample space, okay? And what you're going to end up having is, let's see here, 1, 2, 3, 4, 5. So 2, 3, 4, 5. 1, 2, 3, 4, 5. So 2, 3, 4, 5. Now, if we were to add these bad boys, a 1 with a 1 is a 2, 3, 4, 5, 6. This would be 3, 4, 5, 6, 7. This would be 4, 5, 6, 7, 8. This would be 5, 6, 7, 8, 9. This would be 6, 7, 8, 9, 10. And what we're looking for is those that are greater, the sum being greater than 7. That's these 3 and those 3. Correct? So, how many different events did I have possible? I had 25 events. Because remember, the spinner had 5 numbers, right? So 5 different ways and 5 different ways gives me 25 different ways. Okay, so 25 is that. And how many different ways can I get a sum greater than 7? 6. So simplify that. If you can. But can you? No. That's it.
so then we're not counting like 8 is 1, 9 is 1, 10 is 1. We're counting how many
They're all
times?
different events.
Okay.
Because, hey. What? Yeah, cool. So you'll just say yesterday what title 7 should be? Should have been title 7. Take a look at what form you signed in on though. Okay?
Just matches that one.
It should just match that one.
Okay.
Thank you. Work.
Okay.
What else do you have? Are we good? Anybody else? Going once, going twice? 3 times. You know what I should be having right now? Chamomile. Or a Sprite. All right. Let's finish up our probabilities. Time for notes, Jessica. Get some paper out, Jessica. Which rule did we do last?
2. We're on 3 now. We already did 2.
Is that hibiscus? What is it?
I don't like it when they put like the blackberries in it.
You don't like the strawberries in there?
I said blackberries.
Oh. You know why they call blackberries blackberries? Because they're berries that are black. You know why they call blueberries blueberries?
Because they're purple.
Because they're berries that are blue. Do you know why they call strawberries strawberries?
Is it made out of straws?
Because they're going to end up in a shake and you're going to have to drink it through a straw.
But you can put blueberries and stuff in a milk, or not a milkshake, in a like a smoothie.
I heard a comedian say that. He's so funny.
What comedian?
Joe Wong.
Oh!
I believe it.
I believe it.
You said he's your cousin.
I was kidding.
Don't be playing like that.
I was only J King.
Dude, I can't believe I had to run here.
That's Jason's cousin.
I don't think you ran there at all.
I have this shirt to prove it.
I want to see you run with that backpack on.
Huh?
I want to see you run with that backpack on.
Alright,
I've
for a minute, everybody go outside so
Do
we
you
can watch
want
Prob.
do I need to get the shirt out?
Yeah, you need to
No, I just want to see you run with that backpack on. That backpack is so full.
So was mine. I can
That's
run
why I
it.
had, that's why I had sweat marks like this on it.
You
Mr.
tighten the
Munoz.
straps.
So was mine, but I can still run it.
The straps are really tight.
No, I have doggy.
How much is that doggy in the wind?
You went swimming. I did it.
Bad.
Yeah, I live by Ghost Springs.
You live.
Call me, I would have picked you up.
I used to ride the bus. Who's running like the Terminator? Oh, that's so funny.
Ha! I could see him doing that like the cop. Isn't that the weirdest run though? Like
I used to run like that.
with your hands like this?
Yeah, like this. I was like, wait.
Weirdo.
I don't know how people run like that.
What? All right. So there's samples.
Wait, I thought we were gonna see him run with the backpack on.
He's not gonna do it. He's too tired.
Do it.
Why don't you just recover first?
First, we'll do it later.
Rule number 3. Please quiet down. Thank you. So we know sample space has to add up to 1. Rule number 3 is talking about. Oh, I switched the sign. Rule number 3 is talking about the complement rule. Okay, and the complement rule is simply the probability of some event not happening. Some event not happening. So if I said A is the probability that it rains today, then A complement would be the probability that it does not rain today. That looks bomb. Has it got jelly in there?
Yeah, yeah, something like this.
Is it strawberry or grape jelly?
Why are you not?
Is it red or is it blue?
Grapes aren't blue.
And grape
She
jelly
said-
isn't blue
she
either.
said
You can't
purple.
even justify that. It's
It
totally
looks
purple.
like
Yeah, it looks purple. Everyone sees colors
And it's grape?
Yeah.
That's not even.
No,
the
it's
real
red.
color.
It's red. It's red. It's not.
Well, whatever. It looks bomb though. You really look like you're enjoying that.
Every time we see red jelly, we do that one.
He's like slow eating. You know how they do the commercials?
Me too.
I do it for college, dude.
That was me yesterday. I didn't eat anything the whole day while I was at a competition, and we finally went to Wendy's.
I don't know about you, but when I don't eat anything all day, I don't like slow chew. I'd be like
No,
devouring.
I like to eat
I'm
slow,
like
so
an
I get
anaconda
full.
trying to swallow that whole.
That's just me eating it.
Right?
I get really confused.
All I can think to myself is get in my belly.
No, I try to eat
I
slow
love
because it's better. Like you get full faster.
Why is it so hot in here? They need to turn off the heaters already.
It's like,
It's humid.
wait, it's disgusting. Why is it so hot in here? And he said they needed to cool it already.
Turn off the heaters already.
Oh, turn off.
Why would you turn on a heater?
Wow, that's super cool.
She's trying
Wait,
to
wait,
find
wait,
out.
wait.
I'm really cool.
I know, just bless you. Bless you.
Yesterday, when I sneezed, I had like this brand new tissue, and when I sneezed, it was soaking wet. I was like, whoa. It was just like that. Like, man, that's a lot of snot.
Okay, I typed out my
Hey, being sick is pretty gross. So
the notes.
deal with it.
Hey,
Rule number 4.
Wait,
Okay, let me explain again. For fufu. If I told you that A is the probability, let's see here, probability that you pass, okay, then that means that A complement would be the probability that you don't pass.
Yeah, sounds like me.
So, A complement is simply the probability of some event not happening. So if I told you that the probability of you passing was 0.6, the probability of you passing is 0.6, then the probability of A complement would be 0.4.
Wait.
Because if you have a 0.6 probability of passing,
Oh, I don't know.
it's always out of 1. That's why we go 1 minus. Because remember, probability sample space is always equal to 1. Okay? Now, are there other scenarios possible in this? Probably, but we don't care about those other scenarios. All we care about is you not passing. Okay? Maybe there's a probability of you being issued an incomplete in there somewhere. But we don't care about that. That's still you not passing. That make sense?
So we don't care about these specifics.
Right. All that A complement is saying is it's the probability of some event not happening. Rule 4. If two events are disjoint. Look, let me just explain this really, really simply. Okay? Two events being disjoint means that they are mutually exclusive. They can never happen at the same time. Hey, look at my wet fire. I don't know. I'm trying to
Yeah,
think of
because
something.
you can't have a wet fire.
Not lying.
They came in SpongeBob, yeah.
Okay, SpongeBob is not logic.
SpongeBob is so illogical. It's under the sea and people fall to the ground so fast.
People can literally walk.
Yeah, it's ridiculous. And if you throw something up, it actually comes down, like if there was gravity.
And the fact that fish are talking to each other.
Well, let's not overlook that one.
Wait, nobody cares about that one. You know, that totally happens. Wait, what is it?
Just like if I draw a Just like if I drew a card from a deck. If I drew a card from a deck of cards and I said, hey, look at my black diamond card.
You're like, look at my, let me draw 4 cards. What did you just say?
From a deck of cards, from a standard deck of cards, and I pulled a card and I told you, hey, look at my black diamond. Sir, what deck of cards are you playing from? Because diamonds are usually red. So those should be mutually exclusive or disjoint. Okay? They cannot happen at the same time. I'm not a gambling man. Hey, look, my dog just meowed.
Actually, only surprised because I can have it.
Okay, look, my dog just went a little blood. Everybody knows cows bark.
Oh my god. He was like, you hear it again and he meowed and I was like, okay. And then he said there's a frog in here. You can
I actually got scared by a cow when I went camping, yeah. Well, it was a bull. And I guess over in Sholo, they just let their animals just like go around and eat stuff.
Yeah.
But I had to get up like in the middle of the night and go pee. While I was peeing, I had my flashlight and I could hear something, and I would like look over with my flashlight, and then nowhere.
You're the white
And then-
person in this game with me.
No, I was peeing. I was just like looking around, make sure nothing was there. But all of a sudden, I like hit the light just right, and a bull's eyes looked red in the light, and it was
I don't like that.
bull, and then horns, and I was like,
You're like, uh-oh.
I thought I saw the devil. I ran. That's not funny. That was scary.
I understand you. I understand.
It wouldn't scare you.
Especially after you go. I wasn't expecting red eyes
Yeah,
from a bull.
I used to go to Solo like around July 4th, like you know, there for that, because my friend's family had a cabin up there, so I used to stay with them. And we were like, I was like 9 probably, and we were outside, and there was a bunch of like ostriches like running around down the street, and these people behind them with on like quads and stuff, like chasing them. It was so funny.
Hey Jesse, you ever gone camping? Bet you want to say something too. So, probability rule number 4. Thank you. Thank you. So, probability rule number 4 is saying that if 2 events are disjoint or mutually exclusive, that means they never happen together, and you want to find the probability of one or the other happening, then it kind of follows the same rules always, doesn't it? You just add the 2 probabilities. Now, if 2 events are disjoint or mutually exclusive, and you want to find the probability of A and B happening, okay, think about this logically. These 2 events are disjoint, and you want to find the probability of A and B happening, then what would you do? A and B. And these events are mutually exclusive. No, you do not multiply them. You would say, Mr. Munoz, that'd be 0.
Oh, because they cancel each other out.
No, because they can never happen at the same time. So how can I ask you, hey, this and this needs to happen? Well, it doesn't, Mr. Munoz. They're mutually exclusive. Okay? It's like me saying, hey, you know, a married couple wants to have children, and the first time they have a boy, and then they had a dog. What? No, those things don't happen together, okay? So the probability of having a boy and a dog is 0, okay? They don't happen together.
Well, what if you have because they can't have a boy?
Okay, you know what? You make a fantastic point. The probability of having a boy would be a half, correct? But what's the probability of having a dog? And what would you regularly do? And what's 0 times 1/2? Math works, homie.
That was a serious question.
It was, and I answered it. That's why, because I see where you're going with that, and it made sense. All right, cool. So here's the math form of it. Here's the math form of it. If you're looking at disjoint events, the probability of A and B happening should be 0, should be the empty set. And for the probability of U or B, then it should be the probability of the sum of the two.
Wait, what is that other sign?
Okay. This is, think about this as an A for and. So A and B. And this is actually stands for union, which is or. So you have and, or. Okay? Well, that's gross. That wasn't looking. Oh. And or. Are you asking about disjoint? Oh, I love you. OTT, you got me sick, man. Because you were sick, and you came to see me for tutoring, and I was fine, and then you came, and then I was sick. Thanks, OTT. OTT, I can't explain it.
I just want to. It is.
When I started out running, it was cooler out. It was cool out. It got really hot.
Hey, is it Mike or is it Michael? Is it Mike or is it Michael? Like your real name, your full name. Oh, my bad. All right, we're good? Okay. What is the probability of being married, people? This is a sample space right down here.
Is that all of them?
Okay, so what's the probability of being married? 0.622. Beautiful. What's the probability of not being married? No. Now, this is the example.
1 minus 0.62.
Exactly. This is a complement. Did I get the wrong shade of white up there? Oh, nice. Cheating, bro. Well, it's not cheating. If this is A, then not be married would be a complement. So you'd have to go 1 minus 0.6222. Okay, now that should make sense. If you're divorced, are you married?
No.
If you're widowed, are you married?
No.
No, they're dead. And then never married. So 1 minus that.
So you could add up never married with.
You could add these up, but guess what you'll get? Same thing. Yeah, it's another way of looking at it. But the easier thing would be go 1 minus that. If it's probably of something not happening, then you're safer going that way. But yes, totally right. Okay, cool. How about never married or divorced? Read that through the white. Can you? Is there? Okay. I got the right shade of white. Here's a question for you. Actually, go ahead. What's the probability of never married or divorced? Yep. It's going to be the sum. And this is why probability is hard for some of you. Never married. Okay, so what's the probability of never married and divorced?
0.627.
This is an and.
Let's see.
This is an and problem. So never married and divorced. Zero? Why would it be zero?
There he goes again. He's drinking you.
Okay, there's a little bit more to that. You should say, because Mr. Munoz, those two events are disjoint events. They're mutually exclusive. If you're divorced, that means you were once married. So the probability of being both of those is zero. See how that works? Okay. Don't worry about infinite spaces. This is Benford's law. Benford's law is pretty cool. Benford's law, we won't worry about it. Let's move on through this.
I can see that one.
Ah, here we go.
You got the wrong white.
You had the wrong shade.
What?
You got the wrong shade of white.
Whatever, dude. It'll work.
I see through the matrix.
I see through the matrix. You are the chosen one.
I've never seen.
You are the glitch.
Have you seen these?
Is that what it was? What's the glitch? Is that what they call them? No, the anomaly. You were the anomaly. If an event is going to be independent, this is the definition that I want you to use. The probability, if an event is independent, the probability of A has to be equal to the probability of A given B. That's how that's read. That little bar is a given. Yeah, so if an event is going to be independent, the probability of A has to be the same as the probability of A given B. And when they have a given, that means that that event already happened. That makes sense? So if they give you a given, if you are given a given, that means that event already happened. Okay? So what this formula is saying is if this was independent, it can't be affected by any other event, can it? So if B happens, and the probability is still equal to the probability of A, if the probability of A is still equal to the probability of A, then it should be considered independent. It's like me saying, hey, Michael. Hey, Michael, you're voting Republican. I want you to vote Democrat. And you still vote Republican. Okay? Did my influence have any effect on you? No. Okay. Well, it's a little bit more than that. Because sometimes some events actually happen and they look like they might have some effect on it. But if the probability still matches to its original probability, then it's independent. And I'll show you what I mean by that in a minute, okay? What's under here? May I erase this definition? No? Anybody still need it?
Well, I wasn't done writing.
Okay. Cool. So let me. No, don't worry. I had to write it like this big for Marlene. She didn't have her glasses.
I was so blind.
Yeah, and she's I still can't see what she's doing, so don't even worry about it. I'm like, okay. If A and B independent, probably A and B. That's just the same rule as the and. Here, if they are independent, doesn't matter. If you want the probability of one and the other, then you just multiply the two. That's what it's saying. Okay? It is the multiplication rule. All right. Here are some independent events. A first coin flip and a second coin flip. A coin flip. The rolling of two dice. Choosing two cards with replacement. Is anybody writing these down? This should just make sense, guys. This slide should just make sense. This is talking about independence and the complements of something. So like A complement, whatever, blah, blah, blah. If A and B are independent, then so should A complement and B complement, right? So should A and B complement. And so should A complement and B. Whatever, you know what I mean. I just feel like jumping into a big bean bag and going to sleep. Yeah? Go to your house. Have some hot dogs on the grill. How big is it a love sack?
Have you seen those big ones from IKEA?
That's what they're called.
Cuddle couches?
Those things are huge. Huge. Yeah? But they're so comfortable.
Have you seen those?
Hey, paparazzi.
That was like.
Have you seen those cuddle couches at IKEA?
A what?
Cuddle couches, like a big circle, and then like
Oh, I saw one at Sam's Club. Yeah.
That's where I bought it.
Yeah?
My needle.
Okay.
Can you go back, please?
To here?
Yes.
It's just the pattern. It's just saying that all their complements are independent. Okay.
Stop it.
Mike. It's gonna be a fly landing in your mouth.
My wife makes fun of me because I want to try cricket. What was that? That wasn't yelling. That was weird. Yeah, but you gotta do it like you
I
have
don't
to
want to
commit.
yell loud. The door's open.
You have to commit. That was like. Now you just look weird.
Do it randomly.
Okay, you guys ready?
You wanted to try.
Let's try your skills. I haven't tried a cricket yet.
They're really crunchy.
And I wanted to eat a scorpion. You know, because I've watched the survival shows and you know how they eat everything? It's like, I want to try it. And like, I was like, man, you're going to get sick.
It's just like, if you think about it,
So you wanna try it?
wait, you want
Those
to try
scorpions-
it? Like eating a bug.
Those scorpion suckers at Walgreens.
Oh, I ate crickets before. Those are so dry.
Hey, a traffic light has a probability of stopping you of 0.6. What's the probability of getting through all of 6 lights? Elvis?
Oh, you haven't talked at all today.
Oh, everybody should be doing it. If the probability of being stopped by a light is 0.6 and they're all independent, then what's the probability of getting through all of 6 lights?
24.
What?
That's what I hate about yours. Straighten my hair.
What?
We went to the Daytona.
No, thank you though. Good try. Okay, for starters, you made 2 mistakes. One is you took the 6 times 6, which is not right. Yep. So, right. Now, I know that's gross. Watch it. See it again. What? Manchester? Is that supposed to be like when someone says it again louder? Thank you. I don't have no more phlegm though. As soon as I get more phlegm, I'll do it. I'll make it a nice oil. Be like, Elvis, what'd you get, bro?
I got it. Is decimal okay?
Actually, decimals are perfect. I'm trained to understand those.
0.046656.
I don't know. Let me do it. 0.04.
6656. .6656.
Actually, it's more like .004. Yeah, .004. Okay, now ask why.
Oh, yeah, I know why.
The probability of being stopped is 0.6, and you want to get through 6 lights. So do you want to be stopped? No, that would be a complement. So it's 0.4 times 0.4 times 0.4 times 0.4.
This makes sense.
What? Okay. How many lights are there? 1, 2, 3, 4, 5, 6. What's the probability of me being able to pass the first light? 0.4. How's it 0.4? Well, the probability of being stopped is a 0.6, correct? So that means that if I don't want to be stopped, that would be a complement, and that would be 0.4. So the probability of being stopped is 0.6. The probability of not being stopped is 0.4. So that means I have a 0.4 chance of getting through the first green light, right? That means if they're independent, the next light would also be a 0.4. In order for me to get through 2 green lights, I have to get through this and through this. But I also have to do it through this and through this and through this and through this. So multiply them all out, which is a 0.004. So what is the probability of me getting through all 6 green lights? Sorry, not green lights. Being able to pass all 6 lights? 0! There is, I can't do it. It's not going to happen.
It can't happen.
No?
Yes.
If you pass on yellow.
No.
What number is that, sir?
If I run a red light.
That's .00406.
0.00.
Yeah.
Even if I rounded the 4, that rounds down to 0.
It doesn't matter what it rounds to. It can happen, right?
Nothing.
Vision meeting is like,
I'm gonna stop you.
He's like.
Naked. The probability is 0, my friend.
That worked?
Let's turn this into a real number, okay? A whole number? That means I would have to move it over 2 times for the... All right. There's your good boy. Moving on. You guys need to take a break real quick?
Yes. Want to find a YouTube video for this break?
Okay.
You have a fan?
I do. No. Probably dirty. That'll make me sneeze. And that's the last thing I
Well,
do.
it's not like you have
It'll make it worse. Okay. Thank you. So what you're looking at here in a Venn diagram as a picture is 2 disjoint events. There's no overlap. They can never happen at the same time. To find that probability, you can only find the probability of one or the other happening. And that would be the sum of the 2. If someone asked you for the probability of A and B, you would say,
0.
beautiful.
She said I heard that.
Okay? It's a visual. It's more of a visual for some people that aren't. And it really does help. Here's an example of what I mean. And let me see if I can put my... Okay. These are 2 non-disjoint events. And if you have 2 if you have 2 non-disjoint events, we didn't do them all, did we? And you're trying to find the probability of A or B happening, here's the formula that you're going to use. Now let me explain to you why it's probability of A plus the probability of B minus the probability of A and B. You guys write this down already first, before I explain? You already have it? It's up to you.
It's right there. Yep, I already have it.
Good. Good. sugar. Boop, 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 boop. Boop, 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 boop.
You are my candy girl.
Everybody just stopped. Everybody just went down from there.
Well, you missed a spot.
I made up for it down here.
Yeah.
The purple circle.
That's an ellipse. That's an ellipse.
Is it because it's an oval?
Yes.
Yeah.
Sorry,
What happens
any
when you teach
elliptoid?
people math? Well, I can't talk today.
So, the purple. The purple.
Rounded figure.
Damn. Hold on. The probability. The purple represents the probability of A. This circle would represent the probability of B. But notice that this area was counted 2 times, wasn't it?
Yeah.
It got counted 1 time for the green and 1 time for the purple. That's why we have to take away the probability of A and B once, so that we can eliminate this extra piece right there. Make sense?
Do you like do an example?
Yeah, actually we will.
Deborah.
Okay. So, we have the probability. So there's 2 people that are getting a promotion. Okay. Deborah feels that she has a 0.7 chance of getting the job, and that Matthew's probability of getting the job is 0.5. Now that's kind of interesting. A job in that position. Okay, so it's a job in a certain position. It's not one job only. It's just a position. Okay. Now that's interesting as far as sample space is concerned, because 0.7 plus 0.5, and is that legit? That's not legit. That cannot happen. Okay? Which means that these are not disjoint events. That means that there's some probability of both of them getting the job. Come back to me. What the heck? I know. And that probability is actually a 0.3. It's actually on the next slide.
Oh, okay.
So Deborah thinks the probability of both getting the promotion is a 0.3. How does that affect this Venn diagram?
Why is it 0.3?
What?
Why is it 0.3?
Because she thinks that's what she thinks. This Venn diagram is what she thinks. Okay? So what's going to happen to this Venn? These numbers are going to change, aren't they? Where does 0.3 go? In the middle. These are going to change. What should this become? 0.2.
What? Oh, wait, are you
Because his probability was a 0.5, right? This part represents 0.3 of it,
And we're taking
and that's
2%
0.2 of it.
out of it.
What does this bad boy become?
0.4.
Okay.
You're like the only person I know that actually catches their sneezes. Like, you have the tissue and ready. Like, when I
Try
sneeze,
to.
I have to.
Oh, it doesn't always happen. Okay.
Point three. Let's get these probabilities.
Okay, remember. Okay, I see what you're going with this, Yoda. You're saying that doesn't even make sense because 0.3 plus 0.4 plus 0.2 is only how much? 0.9. Is that the only option available here? No. Deborah getting the job is some event. Was it Mike? Matthew getting the job is some event. Okay? This is the probability of both of them getting the job, right? That's D and M. But there's also a 10% chance that neither one of them get the job. We're good? And that makes all my distribution actually makes sense now.
Is your light or so on?
It might.
Perfect.
Has it always been up there, or have you set up a card that had that on there?
No, it's always there. So now the question was, can we take a look at an example of this problem over here? Okay. So if we know that she had a 0.7 and that he had a 0.5, what's the probability that Deborah or Matthew get the job? Okay. Well, that would be a 0.7 times the 0.5 minus the probability of A and B. Oh, sorry, it's plus. Yeah, my bad. Plus 0.5 minus, and how do you do A and B? Multiply the two. So it should be 0.7 times 0.5. So 7 point. This is going to give me what? 1.2 minus. What is it? So what's the probability of Deborah or Matthew getting the job? 9 point something? Yeah, because didn't you ask me to do an example like this? So this would be Deborah or Matthew. So actually, Deborah and Matthew was a 0.3. Isn't that what we said earlier? It's the probability of both of them. No, not really. Well, yeah, not really. Okay. So that should give us the 0.9 that we had earlier from this. And we said that was going to be a 0.9. So they told us it was. Deborah thinks the probability of both of them being promoted is 0.3.
Is there a way to confirm that, or is it just have to be given?
Yeah, they would have. Now, if you have some limited information, you could probably get some of it. So here's why two-way tables are very big in probability. And let me show you the two-way table. Here's what we knew, right? We knew that the probability of Matthew getting promoted to 0.5, the probability of Deborah getting promoted to 0.7, and the probability of both of them being promoted was a 0.3. And what's really cool about doing the two-way table is that I can figure out everything else. What number has to go here? 1. This is 100% of the probabilities, isn't it? Okay? So if this is a 1, then what's this probability? A 0.5. What's this one? 0.3. What goes here? 0.4. What goes there? 0.2. What goes here? 0.1. And now I filled the whole chart. I can figure out any probability I want. So I could figure out what's the probability of Matthew getting the job and not Deborah. Well, Matthew getting the job is here and not Deborah is here. So what's the probability of that happening? Two-way tables are really cool. I like them a lot.
So the chance of Deborah not getting the job is 0.3.
Deborah not getting the job?
Oh, no. Then why did you do the whole thing?
Because the question was, what's the probability of Matthew getting the job and not Deborah? Well, that means that here we're looking for him being promoted, correct? We're looking for Matthew getting the job, so him being promoted, but not her. So the intersection of the two is the probability of that happening.
But in the other chart, it doesn't add up to 1. It's just 0.4 plus 0.3.
This one?
Yeah.
Yeah, so the probability of Deborah getting the job, the probability of both of them getting the job, probability of Matthew getting the job, and what's the probability of them not getting the job? And that's what we said in the chart earlier. A or B, correct. Well, the other one question was, guys, the other question is, what's the probability of Matthew or Deborah getting the job? So that means they both would have to be promoted, correct? Where? Oh, with the other numbers? Okay, so then so then you're asking the question of what's the probability that, let's see here. We're not looking for Deborah being promoted, we're looking for her not being promoted, right? Which would be a complement and Matthew being promoted. It would be this. So you're changing all the values in there. So let's see here. That means that we would have to take the probability of a complement. So if her being promoted was a 0.7, then her not being promoted is a 0.3. Plus Matthew being promoted was a 0.5. Now this is going to be interesting. Let's see if this works, hopefully. And so then we would look for probability of A and B. So probability of A complement, A and B. What's the probability of A and B? So would that be 0.3 times 0.5? Let's see if this works. Knock on wood. That's a 0.15. So 0.8 minus 0.15 is a 0.65. No, that's not going to work there. Huh. A complement and okay. Let me get back to you on this form right here, okay? I'll get back to you on that one. The two-way one's going to be much easier to read. This is, the charts are going to be way easier to read.
I like the charts.
Yeah, it's not a hard thing. It's just, here, let me show you another one, okay?
Okay.
Oh. Let me make me a note real quick. We would have to approach this very differently, and the reason is, now that I think about it, A complement and B are not, what do you call it? They're not, they don't overlap. A complement does not overlap with B. Over here. A overlaps with B, but not A complement, which is the other part of that. So let me see. Maybe the visual will help. Let me try that one more time, okay? So let's say we had this, correct? So if this is 0.7, then the rest of it is not necessarily point. It's because it's 0.1 here, 0.3 there, 0.2 there. So A complement should be should be 6. Let me get back to you on that one. Let me get through the whole thing, okay? All right. Let's look at another two-way table. What are you doing here? Oh, it's my numbers. Yay. My bad. Okay. Let's go back to the married and the married table, okay? The married table. We're going to add another category, which is the age table, okay? The age table. So you have 18 to 29, 30, 64, 65 and over, okay? Over on the far right, these are called the marginal distributions, which are actually going to be just pretty much the totals of those columns and rows, okay? And this is going to be the total of people that are in this category. So, here's a question. What's the probability of being young here?
What do you count as young?
Well, we have young, middle-aged, and old. So if you're young, what's the probability of being young? Well, how many young people do we have? Out of? And there it is. Whatever that quotient is. Okay? Questions? What's the probability of being married? It would be the 59, 920 over 103 AD. Now, here's the next question. What's the probability of A and B? Of A and B? Yeah, so you're looking for those that are young? So you're looking for those that are young, which is this column, but they also have to be married, which is this row. So the intersection of the two is the number we're looking for. 787, the 8.
Everything in that chart, it makes it so much easier.
It does, and that's why I'm pushing for two ways. I know the formulas are nice, but sometimes they can get really hectic. So when you're looking at this, that should be the 7842 divided by the grand total. You confused? We're looking for being young and being married, right? So this group is young. This group is married. So we're looking for the intersection of the two to divide by the grand total. Isn't that how you do all probabilities? It's desired outcomes over total outcomes. What is our desire? We're looking for young and be married. Correct?
13, 2, 4, 5, 3, 4, 5, 6.
Okay, moving on. Here's a conditional probability. This is a conditional probability. They're looking for the probability of A given B. So what has to happen here? Who do we care about? What if it has to have happened already? They have to be what?
Young.
What's the given? They gave us B. So what has to happen? They have to be married. So do I care about anybody else? No, I only care about those that are married. This is the condition. They have to be married. So amongst those, which are young? This one. So to calculate that probability, it's going to be this number divided by that total. Because do we care about everybody else? No, we only care about those that are married. Understand the conditional probability?
7.64.
I love you. Smile on my face. How about it is. How about the probability? How about the probability of B given A? Oh, I think I skipped it. No white on this one. What do we care about happening first then here? yeah, they're young, has to have happened. So I only care about this column here. And then if they're married, then I would go with this number divided by that total. And that's the probability of B